Hello and welcome to my presentation. My name is Shane Fatehi and I am a first-year master's student at San Francisco State University in the Mechanical Engineering program. I will begin by introducing this robotics course and the instructor, followed by a brief description of what a SCARA robot is. Furthermore, I will discuss the goal of this project and the reason behind using the MathWorks Simulink software, in addition to the Simscape robotics toolbox, and conclude with an overview of the Simulink block diagram used to develop the simulation, followed by several pre-recorded videos of the simulation itself. Engineering 869 Robotics for Spring 2024 was taught by Dr. Azadi. In this course, we learned about the various types of robots such as SCARA, parallel, and articulated, to name a few. We were also given an opportunity for hands-on learning of a common collaborative robot used in the industry and how easily a pick-and-place operation can be taught using the teaching program integrated into the Teach pendant as shown in the image on the right. Additional topics taught throughout this course involved how the workspace of the robot is configured based on the design requirements such as payload and reach, the fundamentals of robot structures by defining the difference between open and closed loop mechanisms, as well as the advantage compliant mechanisms can bring to nano positioning. Furthermore, we dive deeply into the kinematics and kinetics of robot manipulators, such as defining coordinate systems of fixed and moving frames, homogeneous transformations, and forward and inverse kinematics, which were later applied in Simulink. We also learned the advantage of using the Jacobian to linearize the relationship between the joint and end effector coordinate systems, along with how Euler angles can be used to identify singularities. A selective compliance assembly robot arm, or SCARA for short, is an industrial robot used for precise and repeatable pick-and-place applications. The end effector can be fitted with an assortment of designs, such as suction cups and actuators to grasp the object used in the application. Since the robot traverses in planar motion, SCARA robots provide several advantages such as being rigid in the Z direction and having the ability to quickly move to different waypoints while maintaining accuracy and repeatability. The image on the right-hand side is the SCARA robot used for this project, which has 2 revolute joints and 1 prismatic joint. In this course, we were encouraged to use MATLAB to build upon the robotics topics introduced throughout lecture. MATLAB, that is an abbreviation of Matrix Laboratory, is a numerical simulation programming language that is time-dependent based on the given initial conditions. MathWorks is the creator of this software and also has a graphical language using block diagrams that's called Simulink. In relation to this project, MATLAB's workspace is how we assign variables at the rigid body tree that the Simulink software will use to simulate motion of the robot. Simulink is dependent on several toolboxes such as Simscape to define the multi-bodies of the SCARA robot, along with the types of joints used to connect each link. And the robotic system toolbox is used to define the inverse forward kinematics methods and types of trajectories used. An advantage of Simscape is the ability to import computer-aided design files to personalize the physical representation of the robot, using software such as SolidWorks, Pro-E, CATIA, or others. The project requirements began with expanding upon developing a SCARA robot that includes 1 cylindrical base and 4 rectangular links to essentially mimic a pick-and-place sequence by following the waypoint's trajectory shown in the image. The robot consists of a cylindrical base that is connected to the first rectangular link using a revolute joint. The first link is connected to a second rectangular link using another revolute joint, and the end effector that is a welded joint is connected to the second and third link using a prismatic joint that moves along the z-axis. The waypoints highlight the motion of the 3 axes, x, y, and z. The final requirement was to use a trapezoidal velocity trajectory block as the input for the trajectory motion for the given waypoints. Let's take a look at the Simulink model in further detail. On the bottom, we have the final Simulink project file that begins with an input trapezoidal velocity trajectory on the leftmost side that outputs three parameters: the joint position, joint velocity, and joint acceleration, which is terminated since the joint velocity is constant. The joint positions are inputted to the inverse kinematics model, which is represented by the block shown in the top left image. As can be seen, the coordinate transform conversion block outputs a homogeneous matrix that is used to describe the pose of the end effector. The output configuration uses a Levenberg-Marquardt solver with tolerances set at the -6th power for 1500 maximum iterations. The inverse kinematics output configuration is distributed as three inputs to the robot rigid body tree as shown in the center image. Taking a further look, the robot is created in Simulink beginning with the first three initial conditions, such as the ODE solver configuration, the world frame coordinate system, and the mechanism configuration to define forces such as gravity. All three of these conditions connect to the base of the robot initially, which connects to each joint, concluding at the end effector. The robot base is positioned at the center axis using a rigid body transform. The first revolute joint is positioned at the top plane of the center axis using a rigid body transform. That further connects link 1, which is then offset in order to connect the second revolute joint to the end of link 1. Link 2 is connected to link 3 using a prismatic joint, which is how the end effector will translate the z-axis at the different wavepoints. The fourth link is the weld joint that defines the end effector that must also be translated to the correct position using a rigid body transform block diagram. The two revolute joints and one prismatic joint have three inputs from the inverse kinematics model and three outputs that feed joint data to the forward kinematics model, which can be seen in further detail in the top right image on this page. The leftmost block receives the waypoints that are defined in the rigid body tree MATLAB file that are saved in the workspace, and outputs the coordinate transform conversion as a homogeneous transform using the end effector as the source and the cylindrical base as the target. The forward kinematics model sends the joint position data to a scope to present the three graphical representations that will further be discussed in the next slide. This slide demonstrates the simulation of the robot traversing through the four waypoints by capturing several different viewpoints. The top left video shows the top view, while the bottom left shows the front view, and the video on the right top side is the isometric view of the robot. It takes about 5 seconds for the robot to traverse through the four waypoints. The bottom right image is the graph shown in the scope. The top graph is the joint position from beginning to end of the cycle as it goes through the inverse and forward kinematics models. The middle graph is the joint velocity that is output from the trapezoidal velocity profile trajectory and looks similar to a step function. And the bottom graph is the joint position before it is input into the forward kinematics model. And that concludes my final project presentation. Thanks for taking the time to watch, and a special thanks to the course instructor, Dr. Azadi, the Learning Orbis Simscape Toolbox video series, and MathWorks.